Hello everyone, welcome back to our second meeting in Chapter 2. In the previous session, we explored the sense stage of the sense-think-act cycle, where a robot gathers information using sensors. Today, we continue the journey to understand how a robot thinks and finally acts. Our focus will be on two major components. First, the microcontroller as the thinking brain, and the second, the actuators as the muscles that allow the robot to move and interact with the world. Once a robot receives raw data from its sensor, whether it's distance, light intensity, or orientation, something needs to make sense of that information. This is where the microcontroller plays its roles. A microcontroller is essentially a tiny computer on a single chip. Inside it, we have a CPU, memory, and input-output pins. These components work together to read sensor signals, process them according to a programmed algorithm, and then decide what the robot should do next. Think of it like this. When a line-following robot detects that is drifting too far to the left, the microcontroller evaluates the sensor data and decided, okay, I need to slow down the left motor or speed up the right motor. That command is sent to the actuators. Popular microcontroller platforms include the Arduino Uno, ESP32, and Raspberry Pi Pico. No matter which one we use, the logic remains the same. The microcontroller takes input, processes it, then produces an output. So now that the robot has thought about what to do, it's time to act. And that brings us to the next component. Actuators are the devices that turn electrical signal into physical movement. You can think of them as the robot's muscles. When the microcontroller sends a command, the actuators is the part that actually moves something in the real world. In robotics, we use three main types of electrical actuators: DC motor, servo motor, and stepper motors. Let's explore each one. The DC motor is the simplest and most common actuators. It produces continuous rotation at high speed. This makes it perfect for wheeled robots, conveyor systems, or everything that needs constant spinning. However, DC motor spins too fast and with low torque, so we often pair them with a gearbox to increase stretch and reduce speed. To control a DC motor, we use H-bridge driver like L298N to set direction, PWM signals to adjust speed. Example, if the microcontroller wants the robot to turn right, it may slow down the right DC motor and speed up the left one. Next, we have servo motors, which are specialized actuators designed for precise angle control. Unlike DC motors, servos do not rotate continuously. Instead, they rotate to specific position, like 0 degrees, 90 degrees, or 180 degrees, and hold that position firmly. Servos are used for robot arms, pencil camera mechanism, keepers, any mechanism that requires controlled positioning. Servo motors contain a built-in control loop. They have a small DC motors, gears, a position sensor, and a drift inside. The microcontroller sends a PWM pulse with a specific width, and the servo automatically rotates to match the target angle. The stepper motor provides the highest precision among the three. It rotates in small, fixed steps such as 1.8 degrees per step, allowing extremely accurate control. Stepper motors are commonly used in 3D printers, CNC machines, scanners, robotic mechanisms that require exact positioning. Unlike servos, stepper motors operate in an open-loop system, meaning they don't need feedback sensors. They simply move step by step according to the number of pulses they receive. Their strong holding torque makes them ideal for systems that need to maintain position under load. To summarize, sensors allow the robot to sense the environment. The microcontroller processes that information and makes decisions. Actuators transform those decisions into motion. This continuous cycle of sense, think, act is the foundation of all intelligent robotic behavior. Thank you for watching and see you in the next session.